Again, welcome to Math Madness, to Math Meaning, thinking differently about math. Again, my name is Kelly Remajan. I am the Director of STEM Initiatives for the Regional Office of Education number 40 in Illinois. I also serve as Director at Large for the Illinois Council of Teachers of Mathematics. The ICTM is a fully volunteer organization that spans the entire state of Illinois. We have teachers, we have instructional coaches, we have math coaches, we have elementary teachers, middle school, high school, college. We have everything in between all across the state. So if you've never heard of us, I encourage you to take a look at our website, which I'll share, and consider joining. There's lots of opportunities to get involved and also to have connections and resources across the state. So we're going to start off here with some think and talk tasks. Take a moment, if you could look at what you see here. There are 4 items, and the question is, which one does not belong? Which one doesn't belong? So take a moment to think about that. Think about which one does not belong. And when you come up with your answer, make sure you have a reason as to where you can explain why you feel the particular item does not belong. Feel free to unmute and just share what your thoughts are on which one does not belong.
I have 2 thoughts.
Yes, please share.
So my first thought is American currency. So the one in the top left would not belong.
Okay, so we're going to stop
Um,
there for a moment. Awesome. So she said the top left item doesn't belong again because the others have as American currency. And then the question would be, I wonder what kind of currency that is. You obviously know that that's not American currency. Would you happen to know what currency that is?
no, I do
No.
not.
Okay, that's great. Great. Anyone else a different thought or a different reasoning as to why the top left does not belong? Other thoughts?
I thought of a different one. The bottom right, the dollar bill doesn't belong because it's a different shape.
Ooh, awesome. It's a different shape. See, I didn't even think like that. I didn't think like that at all. Awesome. Does anyone else think that the bottom right doesn't belong, but maybe had a different reasoning, a different thought as to why it doesn't belong?
Yeah, it's a coin, or it's paper versus the other 3 being a coin.
Good. Yeah. So that's another way. Again, she had the same answer, but it was different than the first person who said it was a different shape. Interesting. Okay. Um, Ashley says that the top left is European coin. Actually, that is right. Actually, this would probably be from Italy. That is Vitruvian Man, and so that probably is one you would see more often in Italy, but it could be anywhere throughout Europe. Any other thoughts on which one does not belong? Uh, S. Dexter says the bottom left is the only one without an image of a person. Okay, so bottom left doesn't belong. And there again, the reasoning is does not have the image of a person. Interesting. Any other thoughts? Which one does not belong? Now, kind of going along with what S. Dexter said, the bottom left does not have an image of a person, or you could maybe someone else would think of it as it's the only one that has the picture of a building. It's kind of saying the same thing, but in a different way. Ooh, Ashley says the penny is now out of production. So maybe it's the only one. So that one doesn't belong because it's out of production. Awesome, awesome. Oh, let's see here. There's another one in the chat box. Right doesn't belong. And they said that because it doesn't belong because it's worth 25 cents, a currency of 25 units, and the other 3 have a currency of 1 unit. Let's see, any others here? Upper left is the only one without words. Ooh, yes. the only one without words. So it's interesting. We saw things differently. We saw things differently here. Some of us had the same answer, but had different thoughts on the reasoning behind
I was gonna get my
why
jacket,
that was the answer.
but I
And then
did
other
for you.
people saw it totally different and had a different answer. So this is interesting. This activity, I've done this activity with high schoolers. I've done this with elementary students. This activity could be done in a math class, but this activity actually could also be done in a social studies class, a geography class, uh,
Oh, I dropped
all
that.
kinds of history class, all kinds of different classes that can bring math into it. And in Illinois, we're looking at the Illinois numeracy plan that's coming out. It's in draft right now. And that math is a big thing that needs to be brought through, not just in math classes, but in all subjects across all grade levels. And so this is one example of a think and talk task that,
Check was so
again,
fun. I thought it
allows
was
people
too.
to have different thoughts. Their reasonings could be different. They might have the same answer, but they thought of it in a totally different way. The other thing about this question is answers are great, but an answer of top left, top right, or A, B, C, D, or a certain number is
I like
great. What I find
I like the
interesting
different
is the why.
um
Okay, so again, the why is really important. If students come up with an answer, that's great if they have the right, quote unquote, right answer. But how did they come up with that answer? Did they see it differently than other people? And I think that's really, really important. So a think and talk task allows us to promote students with flexibility of thought, flexibility with answers. Sometimes answers we don't have as much flexibility, but the reasoning and how we see things varies very much so. There's really one answer here of how many dots do you see? And come up with an answer, but then think about what is it that you did to come up with that answer. So take a moment to think. And as we know as teachers, that wait time is always important in a class. In a class situation, if I was doing something like this to encourage more students to feel comfortable to talk, I would have them think first, and then I could have them do a turn and talk to each other. The answer is great, but again, how did you come up with that answer? And so a student that might be uncomfortable with talking out in the class, all they have to do now is talk to one person. They're talking to one person to share their answer, to share how they came up with that answer. And if then you give the opportunity for students to share it to the class, either a student shares their thoughts, or if they didn't know, they didn't come up with an answer, they didn't know how to do it, they could reiterate what their partner shared. They could say, Kelly came up with this, and this is how she did it. So it's a great way to allow students that flexibility. How you see this could vary from one person to another. One person said 6 row, 10 column, six. So they're kind of defining what they see. Ooh, then Danelle says 6 times 9 in parentheses plus 6. Now these are numbers, which is great. We can show this with numbers, but having students talk about things is always a good thing. I think somebody said 9 times 6. This is 9 times 6 really should be a parentheses, but when students share those things, you could be putting down, not just having them share it verbally, but putting down on the board or on the screen what it is they wrote. And then we could talk about if someone else might say, well, I thought of it as 9 times 6 in parentheses plus 6. So you could talk about, are these the same? So this is one method of coming up with the answer here of 60. And I love how earlier it talked about columns. One person talked about the columns, the dimensions, and we're going to be talking about that today as well. Another method is actually taking this image and allowing, if you have like a smart board where students can go up and draw how they thought through this. But we could also think of it as taking one from these right column, one and putting it to the middle, and one putting it to that blue top right figure, When we do that, we end up with 10 dots, and we could do the same thing below. We could put one dot with the blue, one dot with the red, one dot with the blue. And so that gives us 10 dots per figure, and I then would have 6 figures, and it still is going to give me 60. And so these are different ways, and we came up with other ways that were shared in the chat box. Students might see, again, the approach differently. They might see the images differently. And so the answer might be the same, but how we get it is different. So taking that concept, again, we can go from elementary all the way up, and I'm going to be showing you some things, how everything connects. If you look at this crayon, how long is the crayon?
6 centimeters.
6 centimeters. Well, my question again is, well, how'd you get it? Some students might say, I just counted. If you say I measure, well, what does it mean to measure? So I started at 0 and I counted spaces 1 to 6. 1, 2, 3, 4, 5, 6. Kind of showing, and not just the answer, but showing the rationale, how they came up with that answer. Another person might say, well, it ended at 6, it started at 0, and I took 6 minus 0, which gave me 6 centimeters. Different ways of looking at it. And some people might say, well, I just know it's 6. I just know it's 6. And that probably a lot of us would say that. And our students are going to come back and say, well, I know it's 6, but how do you know? How do you justify? What is it? How do you see this? So if we take that same crayon and we move it over, how long is that crayon? Bonnie says it's 6 centimeters. How do you come up with that answer? To me is the interesting part. Ooh, Danelle says she found the difference of 14 minus 8. 14 minus 8. Well, how did we get 14 and how did we get 8? Because we started with 6 minus 0. Oh, I did say it was the same crayon. You're right, Pam. That's exactly right. I just moved it. I translated. I transformed it. I slid it over. These are terminologies. These are terms that lead you into high-level math. I just moved it. How far did I move it? I moved it 8 places to the right. I moved it 8 places to the right. And that is 14 minus 8, which is still 6 centimeters. So this concept of taking something that is very elementary with measuring and then thinking about how we move it can lead to other ways of thinking, can lead to other concepts. So taking this idea, if you have a problem like this, subtraction, how would we go about subtracting this problem? How would we solve this problem without borrowing? Because most of the time, I know that that's what's being taught. Is it okay if a student thinks about doing this a different way? Maybe they struggle with borrowing. Do they have to borrow? That's a question of, we can think differently about this problem. Now, the individual on the right, his name is Howie Wah. He is a fantastic person. If you do any social media following, I would highly recommend that you follow him. He is phenomenal. So I'm going to be showing a few things about him in this presentation because he's fantastic and he really shows a great job with this. So I'm going to show you a little
Now,
video.
it's totally okay if you did something different than what I did here. But for me, I added 3 to both numbers because 88 minus 30 is much easier than 85 minus 27. Now, we can see visually why this strategy works. We can think of subtraction as what's the distance between these two numbers on the number line. So if we start at 27, how can we get to 85? And we can see that if we add 3 to both numbers, the distance is preserved. So some people call this strategy constant difference, and others call it same distance, same difference.
So I used a ruler. He's using a number line. And so again, it's a little bit different thought process, but we can come up with that answer. If a student does borrowing and still gets the same answer, fantastic. It's what is it that makes sense to that student. But if we look at it in a different way, it allows us to make connections to other topics number lines, transformations, just a different way of looking at it.
Now,
So if we go back to old school, we have this old school problem of borrowing, a different way of thinking, a problem like this. Instead of adding a number, like we did with the crayon and with the previous problem, we could think of it about subtracting from each of these numbers. And then we can simply subtract, which then we don't have to do any borrowing. And so again, this is taking that crayon. If we originally started where we ended up, if we moved it to the left, we can move it left or right, that crayon. And it's a matter of now, it's a difference of where the crayon starts and where the crayon stops. And so again, different way of thinking with subtraction without borrowing. Answer here is still the same as what we got initially. Now, in math, converting mixed numbers to improper fractions. When we have this, we probably will just teach our students that we multiply the numerator, or we multiply the whole number by the denominator, and then we take that result and we are going to add 3 to that result, and we're going to get our final answer of 11 over 4, and we move on. Great. But you might have students that, first of all, might struggle with this, understanding what to do, but they might struggle simply because they don't understand why that works. Now, some people don't really care. Just tell me how to do it and I'll do it. However, what we have now with technology, that technology can crunch and do calculations for us, and it's going to become more and more. We really need to think about the thinking, the deep thinking, the being curious. Why do these things work? That is becoming the most important thing, because we can ask the computer to do something for us, or we can ask a question. The problem is we got to come up with the questions, or the students should come up with questions that they can pose, that they can seek out those answers to. And that curiosity is really, really important. And so here we have, again, we have the answer, but here is just an example of a video that shows why this is my answer. And I would encourage you, if you do any follow of social media, and we know with Facebook, if you start following or watching things, that because of that algorithm, you're going to be fed certain things to you. So you're going to have things pop up. That's all math related. And that's interesting. Technology is based on math. And there's a lot more to math than simply crunching the numbers. So when you watch these videos of people on the social media, videos, whatever, I would encourage you to reflect on what they're doing. And how would I do that? Is that a good way to do it? I don't think I would do it that way. I like that, but I don't. And I think us as teachers analyzing others, because we don't usually have a lot of time to go into other classrooms and observe people. But if we can watch videos online, we can have a chance to, I want to say critique, but reflect what others are doing. And is that something that we might consider, or hacking, if you will, what's being done to do it in a different way that will help my students, that'll make more sense. So take a look at this video here.
The denominator of 4 is telling us that we're looking at a whole number that is split into 4 equal parts. The 2 is telling us that we have 2 wholes. So we have 4 quarters, and then we have another 4 quarters. So now I'm going to draw 2 fraction bars to represent 2 of these wholes.
And then we have pictures that are representing.
Now we're going to look at 3 quarters. The numerator of 3 is telling us that 3 out of those 4 parts are shaded. So I'm going to draw a fraction bar to represent 3 quarters. Now the next step is to count how many quarters are shaded. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 11 quarters shaded.
So watching this video, something that also sticks out to me is the term of quarters. So we have 11 quarters. And so I would ask, Do you say quarters or do you say fourths? That would be something something to reflect upon. If you say it one way, is that an easy thing just to also say fourths, 11 fourths, or 11 quarters? Chances are, if it's somebody from Europe, they're probably going to say quarters. US, it could be either, but I find probably a lot of times it's fourths. And it also might depend on your level that you actually teach math. So just a quick thing in the chat box, if you will. Do you say quarters or do you say fourths? That's again just something to think about. I'm curious what people say, or if they say both of those things. Fourths, fourths. Again, most people in the US are going to say fourths. And Danelle says, she says both on purpose. And I think that's a good point, that if we're saying it one way, maybe we can easily simply say it another way. Quarters, 11 over 4, 11 fourths, or 11 quarters. Now, when I looked at this social media person when she explained it, there were some things I did not like about how she was explaining. And so if I took that, I might take what I saw and make some changes. And so when I see this, I think of this as two makes I have two, I have one whole plus 3/4. All right. I'm thinking, what does one mean? If I'm talking about fourths, that means 4/4. You could be talking about this. Again, it's slightly different than what this person did on social media. But again, showing it in a different way, that analyzing other people's work, what's good, what's something you would do differently, I think only makes us better teachers, and looks at vocabulary, looks at how we say things or how we show things or how we organize things. Again, all of this helps to look at things in a different way. And so we still are going to get 11 fourths for this result. No matter how you look at it, you're going to get 11 fourths or 11 quarters. Now, another topic, having numbers. So how do you take half of a number such as 68? So again, we could get the answer, but my interest is, how would you go about, or how would you teach your students how to take half of a number such as 68? So feel free to share in the chat box, how would you take half of this number? Again, we could get the answer, but the interesting part is, even for what might be simple problems, depending on your grade level, it could be simple, it could be something that is advanced. How do you take half of a number such as 68?
I have them break down
go ahead.
the number into like 60 plus 8, and then find half of each of those, like half of 60, half of 8, and then adding those two numbers together.
Awesome. Very good. So that's one way to do it. Fantastic. Ooh, so different ways you can see in the chat box. All right. They're both even, Denise says, so half of 6 and half of 8. So meaning to divide each by 2. And so there's different ways we could do it, but there's different strategies. This strategy fails with odd values. Exactly right. And that's the good point to make, is this works, but does it always work that way? As simple as that. So now if we had a number such as 37, how would we do that? So interesting what was said earlier. Social media math influencer, Sums of Anarchy, which I love that name, Sums of Anarchy, she actually talks about how to have numbers 5 different ways. So I'm just going to show you a little bit. I also want to show you different clips of people, because we are all different people. Your students have different experiences. They may have had someone who's very energetic, someone that maybe is just kind of monotone. They might have had a man as a teacher in the past. They might have had a woman as a teacher. We're all different. We all have our positives and our negatives. We all have our strengths and our weaknesses. And so I'm going to be showing you 3 different social media influencers as well that talk about some of the things we're discussing here. But again, this is Sums of Anarchy. She, you can tell, is probably not from the US. So let's take a look here.
Is Here's the thing, there are many different strategies when it comes to maths, and what's best for some of us isn't necessarily best for others. But if we allow ourselves the freedom to play with numbers, to use them flexibly, to accept that a method is only better if it's better for us, we'll grow in confidence and we can explore other strategies which may be more efficient when we're ready for them. Eventually, we may look at 37 and feel good about breaking it into a 30 and a 7, halving those separately to give 15 and 3.5, then adding them back together to give 18.5. Maths isn't a collection of unrelated events. It's a series of ideas that builds upon the last. So if something feels tricky, there's usually a way to break it down into something that's more manageable. If we find the methods that will meet us where we are, we'll ensure that even the odds will be in our favour.
So this, and I apologize, I don't remember who said it earlier, this kind of goes back to one of the strategies that was used with 68, breaking 68 apart into 60 plus 8, and then taking half of each. Half of 30 is 15. You know, we could take half of 50, which is 25. And so there's different ways we can approach it. But again, this is a different way of looking at taking half of a number, whether it's even or odd. Now, also with Sums of Anarchy, this is something that I really never thought about until I saw this. And I'm like, oh my gosh, that's totally, why haven't I never said this before or even like thought about this? And that is that percentages are reversible. And I love this because it brings in other concepts when you're, instead of just, okay, this is how you find percentages. It allows then students to think differently. You know, why can we say percentages are reversible? Why is that? You shouldn't believe everything online on social media. Is this true? Are percentages actually reversible? Are they? Well, let's talk about this. What does that mean? So if percentages are reversible, that would mean that 16% of 50 would be the same thing as 50% of 16. Interesting. Again, I've never really even thought about this before. So, but why? First of all, is this true? And if it is, why is this true? Why does this work? And so talking about this, again, there's a lot of math then, a math discussion that can occur on why this works. Again, the why is important, not just an answer, but the why. How did you come up with that? And so if we look at 16% of 50, well, what is 16%? 16% can be thought of as 16 over 100. That's what percent, 16% per century, per 100. Of can be multiply. So we have 16 times 100, or 16 over 100 times 50. Now, 50 is the same thing as 50 over 1. And because I know that multiplication is commutative, that means I can switch, instead of taking 16 times 50, I can take 50 times 16. And if I look at this, 50 over 100 is really the same thing as 50%. Times is really the same thing as of. And 16 over 1 is really the same thing as 16. And so this shows why percentages are reversible. And again, I like that because it really gets into the math behind. And again, it brings you into other things, and it rolls that math conversation and topics all back for discussion. And there's more of these practice. I love that Sums of Anarchy has like a really quick, like they'll have like 10 problems of different topics, and it shows the problem. It gives a certain amount of time. And we're not wanting to, again, have students do things quickly, but having students think about things and then to practice what they came up with as their process of coming up with an answer, I think is important. Another topic that allows us to make connections into other concepts beyond multiplying is when we can multiply using rectangles. So if we have 8 times 15, we can think of it as a rectangle that has dimensions of 8 by 15 or 15 by 8. And that goes back, we could say 15 by 8 because multiplication is commutative. Now, if we have 8 times 15, we can think of 15 being broken up into 10 plus 5. That kind of goes back earlier when we said we'll take, let's say, 68, and we can break it up into 60 plus 8. Here we can take 15 and break it up into 10 plus 5. And when we break it up into 10 plus 5, we can really think of this as the sum, the two areas of these two rectangles. And so we would have 8 times 10 is 80, 8 times 5 is 40, and our total then is going to give us 120 square units. And so I think the important part of a lot of people will be very negative, possibly. I'm not saying educators, it could be just people from the community that say, this new math, why are they teaching all this new stuff? Now, some of this stuff you might disagree with, but certain things I think have great connections that lay the foundation for other topics. And so when we're looking at something like this, there's a connection with matrices. Again, if you're elementary, even middle school, you're not doing matrices, but this leads to matrices high school. If you're teaching 8th grade, you could actually get into matrices in 8th grade. And what that matrice connection is the number of rows by the number of columns. And so when I do these kinds of problems, I like to have the first number being my rows and then the second number being my columns. And because that is how it is denoted when you're doing matrices. The dimensions of a matrix are written by the number of rows, by the number of columns. The second part here is a connection to distributive property. Love this. Again, this leads the connection to distributive property. It shows why it works. It's the connection to something visual. Talking here, I love that Michael said, he said we began to use rectangles for factoring and multiplying polynomials. Exactly, I'm going to be showing that as well. And he says it's more visually appealing to the students and gives students something to anchor to when they get stuck. Exactly. Visual cues, visual people. A lot of students that I've had in the past, when I had them in algebra or then I had them in geometry, and I don't know where this is coming from, but they'll say, oh, I'm not good at geometry. Or I was better in algebra, or whatever they said. I'm not sure where they're coming up with that thought process, but if they think they're better at geometry, giving them something visual and simply saying, hey, this is connected to geometry is a great way to approach it and giving them that confidence that they can build off of their strength, which might be geometry, might be something visual. Again, this is a screenshot for one of Howie Wah's Reels, Facebook Reels, and this shows how you can do this not just by one digit number times a two-digit number, but you can do this with a two-digit number times a two-digit number. You can do this with two numbers that are fractions, and you could also do this with two binomials as well. And so this leads into a FOIL, which is really just simply distribution. And so again, this is the connection to multiplying using rectangles. Again, love the connections here that we can build off of, and we can refer back to things, or we can highlight certain things that will help students in the future for what they're doing. Again, connection to FOIL. So more with rectangles, and that is with solving equations with rectangles. And so you could have just pictures. If you have something like this, and this kind of goes back to what we started with at the beginning of this session, was with that ruler. We have a ruler. You know, if we have something that's 15 units long and we have something that's 11, and well, how much does that other part have to be for that whole entire object to be 15? You can think of it as a ruler. You can think of it as simply rectangles. And so here, students can kind of rationalize what that answer is. They can also potentially set up an equation just to make that connection of what that looks like as an equation. And so what is the only number that would make this work? What number plus 11 would give us 15? And that is where we get that answer of 4. Again, we're talking about rectangles. We're using those visual cues to do algebra. Another one here, same thing with setting up an equation and then solving. This comes from a social media resource called Super Teacher Guy that I want to show you. Again, I think it's important to look at different social media influencers. His particular connection, he does a lot of tutoring, but he also does a lot of work with parents. And so making the connection, if you had resources that you could share with parents, that maybe then they could help their student also, and that this parent can then get a more positive outlook on math. Because a lot of times, sometimes people will say that math is, whether you get it or not, is genetic. I disagree, but the mindset that could be passed down definitely carries. So if a parent says, well, I was never good at math, then that's probably what's going to be said. The student then is going to say, well, I'm not good at math either. And maybe that's what they've heard. Their parents or whoever they live with is saying that they're not good at math, then they're going to say that same thing. So looking at math in a different way could potentially help. So here's Super Teacher Guy. Just want to give a quick glimpse of him.
Bar models, aka equiligrams, represent so well addition, subtraction, multiplication, and division. It can be used in pre-algebra class. It can be used for 4-year-olds. It works across all ages. That's why it is so beneficial.
You notice he said something about equiligrams. That was something that I had never really thought of or heard of before. So again, different terminology that might be used. So more a little bit, just quick with rectangles here. Just wanted to point out again, if you start it with the equation, having students represent it visually, what that means, and then rationalizing it. What would X have to be if they all are going to be same? And then they kind of I would take 15 divided by 3. So they're kind of rationalizing how they would get the answer without the process of we're going to divide both sides. They see it for themselves. I can take 15 and divide it by 3 to get my answer. Same thing over here. I have 3 parts. 1/3 of X is 15. And so to get the total, how would I do that? If they're all the same, I'm going to take 15 times 3. And so they can see that I can just multiply. That's where I'm multiplying both sides by 3. A little bit more with this is just examples of how you could take this more steps with that process of thinking it through without necessarily going through the formal steps of kind of having them rationalizing it first and then showing them the steps that correspond to get your answer here of X equals 7. Another resource tool is Polypad, where you could have students use a balance scale. And this is free through Polypad. You just get a balance scale. In this video, you'll have access to. And then they can do it if you actually have a scale or just electronically. You can pull out 2 X's. Those X's could be vertical or they could be horizontal. You could have a -3 where you go to numbers. And then if there's the negative, you could just type in a -3, which will come out as red. And so that's one side of my scale. And that's going to be equal to 7, which I'm going to say is equal. And so now you can kind of see, okay, if I add 3 to one side, I got to add 3 to the other. Oh, wait a minute, that's 0. And 7 plus 3 is really the same thing as 10. So, well, wait a minute. If I have X and X equals 10. Well, 10 is really the same thing as 5. Letting them rationalize through this, thinking it through. Letting them see it. Again, instead of giving rules, having students the opportunity to see things differently. Because if they see it, if they think through it, it's going to be more meaningful. They're going to be more confident, and they're going to be able to go back to the method that they see, that makes sense to them. So in this case, X is going to equal 5. Again, this is Polypad, free resource online that you have a balance scale access to. Desmos, this would be more for 8th grade and up. Solving the equation 2x minus 3 equals 7. If you're teaching 8th grade or high school, I would highly recommend starting to use Desmos because Desmos is being used on the ACT and it's a game changer for the ACT. And so solving this equation is really just graphing 2 equations, graphing the left side as y equals 2x minus 3 and the right side is y equals 7. And we want to see where these two lines intersect. We want to know what is x when y is 7. And so x is 5. And so this is a way to solve equations simply using Desmos and graphs, graphing with Desmos. Great tool. If you haven't used it, I highly encourage 8th grade and up to start using Desmos. Now, understanding long division. This is an interesting thing. And a lot of times we will show students the process of how to do something. And it's just, I am a robot. I'm going to do exactly what I am told to do without really thinking. And so I think it's important to understand long division with context. So I'm going to show you a little video here with Howie, and then we're going to talk a little bit about your thoughts. Also, pointing out when you do watch things on social media, it's always interesting to see what comments are from people, that you'll have positive comments and you'll have negative comments. And just a side note here, on one of his recent posts, it was very interesting. He does all this free and he's phenomenal. He actually made a comment that he didn't know if he was going to do this anymore because of all of the negativity that's out there, which I think is sad. There's a lot of, I see a lot of positives, but the fact that he said that on a recent post was it's very much saddened me. And so if you do watch any of his videos, I would encourage you to post positives, or post in a way that is not like hurtful when you do watch these videos. So let's take a look here and then we'll talk.
The long division algorithm can be understandable and not just something to memorize. Here's how we can make sense of it. Let's use the example 532 divided by 4. We could think of this as if I have $532 and I want to split it with 4 people evenly, how much money would each person get? Now the first step in the algorithm is to ask how many 4s fit into 5. 1. 1 times 4 is 4. 5 minus 4 is 1. Now in context, we could think of this as if I have 5 $100 bills, each person would get one $100 bill, and I would have one $100 bill left over. Now the next step in the algorithm is to...
So I'm going to stop there for a moment so you can see each person got 100. Each person got one $100 bill, and we have one $100 bill left over. So again, that makes sense. Okay, got it.
Bring down the 3. But what does bring down the 3 mean? Well, with the $100 bill, I can't just rip it up into fourths and give each person a part of it. I would need to exchange that $100 bill for 10 $10 bills. So in total, I would have 13 $10 bills. And with 13 $10 bills, I can give each person 3 $10 bills, and I would have one $10 bill left over. Now, the next step in the algorithm is to bring down the 2. And we do this because I can't do anything with this $10 bill. I would need to exchange it for 10 $1 bills, so I'm seeing this as 12 $1 bills. And with 12 $1 bills, I can give each person 3 $1 bills. And in the end, I can see that I can give each person $133. So the long division algorithm can be understandable, and not just something to memorize. All we are doing is sharing equally, and when we bring down a number, we are exchanging for the next place value over.
So some of the comments for this video you'll see on Facebook. One of the negative comments is that it's confusing, and that's that whole just do it thought. Again, some students, some teachers just, let's just do it, and that's fine. But I think we're missing opportunities for greater understanding if we just have students do it. This person then kind of responded to that, the fact that somebody said just do it, as a way to kind of explain. It might be the just doing it might not be helpful to a struggling student, but I also have to say for some gifted students, they actually might struggle with this as well. And I would say I was never a gifted person by any means, and I'm still not. But how my mind works is I want to understand how things work. Maybe I was supposed to be an engineer because I want to know how things work. I don't know. I'm not an engineer, but if I can't understand where that came from, my mind kind of shuts down and I can't pay attention to other things. And so I'm trying to figure out why does that work? I don't understand. I understand how to do it, but I don't understand why that works. And so I think we need to think about this for not only our struggling students, but also our advanced students and allowing them to understand what's going on here. And so we don't want to just have students do it. Again, technology is going to do stuff. It's that curiosity that we want to promote that's very important. Curiosity. Another point, another person, Grace, commented about some people say it's dumbing it down. This person said it's not dumbing it down, it's showing the why. When we know the why, it helps to do the work. Again, the why. Again, some people will disagree that it's dumbing down. This person shows a connection, and this helps us with polynomial long division in Algebra 2. So it makes a connection for later math classes, later concepts. And I think that's the point that we need to think about is what are we teaching? How can we look at it differently where we can then make connections that we can then, whether we're teaching things now and pointing things out in the future, laying the foundation, or if we're teaching advanced things in Algebra 2, we can refer back to that topic that helps students to make connections. But with your thoughts with this, just reflect. You don't need to put anything in here, but reflect on this, on what your thoughts are. This all goes in evenly, but how does this work if they all can't get a dollar bill? And that's where we have change. And so that's something that could be talked about. But money is always a great way to make connections. But I will say that we're going to find that that's going to become harder and harder as more people are not using money. They're using credit cards or other means with tapping phones and such on money. But I still think money is a good connection because students, at least high school students, I can say, they always become interested in making money as they get older. So something to think about in terms of understanding long division with context. Adding integers. Now with adding integers, again, we can give rules. And rules can often be confusing. And so I think having an opportunity for students to manipulate with actual objects or technology is a good idea. So something like this, we have 4 positives, we have 5 negatives. Every positive and negative pair can drop out and make 0. And again, this might be simple, but the next one is where I think this really comes into play with understanding. So again, every positive and negative pair is 0. So those cancel each other out because they're 0. They cancel each other out, and we're left with 1 negative. And that's why our answer is -1. So instead of giving rules, allowing students to see things and to see for themselves as to why that's the answer. Now, when you get to 3 minus a -2, I know that a lot of teachers might teach this as, and if you do, that's fine. I will say this always drives me nuts. When I've heard students come to me and say, well, my teacher in the past said something like copy, change, or something like that. I'm like, what does that mean? Students have no idea what that means. They just don't remember. They memorize copy, change, or there's something else. I can't even remember what it is. But 3 minus -2. So if we have 3 minus -2, I have to have 3 positives, and then I have to take away 2 negatives. But to do that, I have to have negatives, and I have to remember that every positive and negative pair is 0. So I can bring down as many different positive and negative pairs that I want. So if I bring one pair down and another pair down, I now have 3 plus 0, which is still 3, minus, I'm going to take away 2 negatives, and then that's going to give me my answer of 5 positives, or a positive 5. And again, the understanding of what's happening, maybe you never saw this way, but it's a different way of looking at adding and subtracting integers. Fractions. This is a great tool from Polypad again that is with fraction tiles. And so if you want to add or subtract fractions, whether you're adding or subtracting fractions with the same or unlike denominators, it's important to understand equivalent fractions. And so if you have 1/2, well, 1/2 is equal to 1/4 plus 1/4. You can see when you look at these fraction bars, 1/4 plus 1/4 is directly under 1/2. Now, some students would say that 1/2 then is equivalent to would be equivalent to 2/8, because they would add the top numbers and they would add the bottom numbers. But if you look at the screen here, 2/8 is this, which is not equivalent to 1/2. What I have, though, is 1/2 is equal to 1/4 plus 1/4, or 2/4, or 4/8, not 2/8. It's a way for them to see things for themselves, to see it. And hopefully it makes a little bit more sense. Others you could simply do with 1/2. 1/2 is equal to 3 of these 1/6, 3/6. 4/8. I can see it's equal to 5/10. Again, these are fraction bars that you can use to help students see something different. This is a video that I really like for you, but I'm going to start showing it because it uses fraction strips, and we're adding, or we could subtract with unlike denominators. And you could use fraction strips that you actually print out, laminate, or you could use virtual fraction strips, or you could use polypad again with fraction bars. So just to start this off just a little bit.
To add 1/2 plus 1/5. We can't add two fractions with unlike denominators. We can add these fractions by converting the denominators into like denominators. We'll do this by using fraction strips. We'll put the 1 whole as a benchmark to see if our sum is less than 1 or greater than 1. Now let's put the 1/2 strip and the 1/5 strip next to each other. To find the common denominator, we're going to use multiples. Let's list the multiples of 2. 2, 4, 6, 8, 10, and so on. Now let's list the multiples of 5. 5, 10. As you can see, both lists have 10. So 10 is our common denominator. This means that we'll use the strips with 10 in the denominator. Now we line up the 1/10 strips under the 1/2. 1, 2, 3, 4, 5. So 1/2 is equal to 5/10. Now we'll line up the 1/10 under the 1/5. 1, 2. So 1/5 is equal to 2/10.
And so again, this gives a visual on the fractions and using these fraction strips or fraction tiles or fraction bars. Multiplication, kind of talked about this earlier. What does multiplication mean? And this kind of goes with rows and columns. It goes with repetitive addition to get answer. And this then leads to multiplication of fractions. And so making that connection of 2 times 3 and your dimension. So if I have 1/2 times 6, if I started off with 1 by 6, I really want 1/2 by 6. And if I think about it like this, now it's repeated addition. I have 1/2 plus 1/2 plus 1/2 and so on to get my answer, which is 6/2, 6/2, or 3 for my answer. So it gives that connection, making the connection and giving different ways of looking at things that bring everything together. A multiplication of fractions, just kind of go through this. 1/2 of 1/3. So I have 1/2 of 1/3. And my answer is where the two bars are going to intersect, which is going to give me that green part, which is 1/6. So again, gives us a visual on multiplying fractions. There's some more here with fraction tiles that could be used. And again, you'll have slides for all of these that you'll have access to that gives you some more examples of how to do division with fraction tiles. And I like this because it leads into, well, what do we do when we don't end up with a nice answer? There has to be something. How do we deal with something like that? So building on things, but allowing students to see, hey, it's not always going to work. Another way of looking at division of fractions is an alternative method, because a lot of people will teach this as division means multiply by the reciprocal. Well, another way of looking at this is to simply get like denominators. Most people don't teach it that way. And if we get like denominators, once we have like denominators, we divide the numerators, we divide the denominators, just like we would be doing across with multiplication. And so here we get 3/5 over 1, which is really 3/5. So this is maybe a different way you thought about it in the past. Instead of teaching as division means multiply by the reciprocal, we can think about it in a different way. Again, there's a video here you could look at with Howie. And last, making math more visual. There's a whole site with different visual cues that allow students to see the mathematics that's happening. And you have a source here. Here you could ask students, what do you notice? What's happening here? What's the pattern that you see? And so in the first picture, I saw 3 objects. In the second object, I saw 6 objects. In the third, I saw 9. In the fourth, I saw 12. You might see things differently, but allowing students to see different things and allow them to recognize patterns and build off of those patterns. And from those patterns, this actually can lead into, that first part could actually be elementary. The second part here leads into algebra and equations. And so when you have an x value of 1, a y value of 3, and so on, we really have an equation of y equals 3x. This is a linear regression. Again, this leads into higher level mathematics, allowing students to see things, asking them what they see. Well, I see a bunch of green squares. Allowing them to say that, I see an L shape. Oh, I see 2 L shapes. I see 3 L shapes. They might see it in different ways. Today, I hope you got some feedback on ways to promote thinking differently about math. We talked about 3 social media influencers, and there are other resources that I've listed if you'd like to take a look at to get ideas on how to promote thinking differently about math in your own teaching, as well as within your learning and your understanding for your student. I am available if you want to shoot me an email at any time. I'm more than happy to answer questions as to this session as well. Again, I hope you got something out of today. Teachers have a hard job. We truly do. And one thing we can do is to really help each other. And that really, the Illinois Council of Teachers of Mathematics is all about helping teachers. And that's kind of my goal, is to always help teachers. And teachers are the ones helping students.